Our goal is to find the interval of convergence for the following series. Let us begin. Remember that to find the interval of convergence, first we need to use the ratio test. For the ratio test, we are finding the limit of the absolute value of an plus 1 over an as n goes to infinity and it's equal to L. This L must be less than 1, so we have a convergent series. A convergent series. Very good. Let us begin. This is your an. This is the general term. Everything that you see here is an. So we are finding the limit of the absolute value of an plus 1 divided by an as n goes to infinity. So you get the limit of, on the numerator, you have 2 to power n plus 1 x minus 3 to power n plus 1 divided by square root of n plus 4. And on the denominator, you copy down your an. Let me use a different color for that. 2 to power n, x minus 3 to power n divided by square root of n plus 3 as n goes to infinity, which is equal to the limit of the absolute value of 2 to power n plus 1 x minus 3 to power n plus 1 times square root of n plus 3 divided by 2 to the n x minus 3 to power n times square root of n plus 4. Let's close up the absolute value as n goes to infinity, which is equal to, so you can simplify this using a little bit of algebra. You have the limit of the absolute value. All of these numbers are basically positive. You just need to be careful about the x minus 3. So you have 2 to the n times 2 to the first power, x minus 3 to power n times x minus 3 times square root of n plus 3 divided by, let me move this a little bit here so I have enough space. Let us close up the absolute value as well. N goes to infinity, and on the denominator you have 2 to the n times x minus 3 to power n times square root of n plus 4. Well, you can cancel out 2 to the n, 2 to the n, x minus 3 to power n, x minus 3 to power n. So you end up with the limit of the absolute value of 2 times x minus 3. Good, we simplified this to a very nice quantity times square root of n plus 3 divided by square root of n plus 4. Which can be written as the limit of, well, here you have square root of n plus 3 divided by square root of n plus 4, which is 1, as n goes to infinity, times 2 times the absolute value of x minus 3. Very good. So this limit is equal to 1. We don't have any issue with that. And this guy, based on the ratio test, must be less than 1. This is what you're dealing with. Okay, so you have 2 times the absolute value of x minus 3 less than 1. If you divide everything by 2, you get absolute value of x minus 3 less than a half, or x minus 3 is bounded between negative a half and a half. And x is bounded by 3 minus a half and 3 plus a half. Very good. So your x is bounded by these two numbers, 7/2 and 5/2. But the question is that, what about the boundaries? So far, we know that this series is convergent on open interval 5/2 and 7/2, but we don't have any information about boundary points when x is equal to 5/2 and when x is equal to 7/2. We need to check this manually. So let us begin. When x is equal to 5/2, our series becomes, let's take a look at our series. So let me copy this guy down. Our series becomes the summation of 2 to power n. Let me just simplify this and write with the same color, just change x value so you see what we are doing, and start from 0 to infinity. 2 to power n, your x minus 3 to power n divided by square root of n plus 3. This guy is just 5/2. So you get the series of the summation of 2 to power n square root of n plus 3. So you get -1/2 to power n, right? -1 divided by 2 to power n, which can be written as the summation of 2 to the n, -1 to the n, divided by 2 to the n, everything is divided by square root of n plus 3, and start from 0 goes to infinity, so you can cancel out 2 to the n and 2 to the n, and you end up with alternating series. This is -1 to power n divided by square root of n plus 3, and start from 0 to infinity. This series is an alternating series. This new series, when x is equal to 5/2, is an alternating series. So for an alternating series, remember that the behavior was the summation of -1 to power n minus 1 bn, and start from 1 goes to infinity when bn is decreasing. And the limit of bn as n goes to infinity is 0, then we say that we have a convergent series. You can check this. For an alternating series, here you can easily check that since Bn is equal to 1 divided by square root of n plus 3, the derivative of Bn is equal to 1 divided by square root of n plus 3 derivative, which can be written as n plus 3 to power negative a half, which is negative a half times n plus 3 to power negative a half minus 1, or negative 1 divided by 2 times n plus 3 to power negative 3 halves. Or this guy is negative 1 divided by 2 times, here you have the square root of n plus 3 to power 3. This is always positive. But since you have negative 1 on the numerator, it is negative. So the derivative is negative. Since the derivative is negative, since the derivative of Bn is negative, it means that Bn is decreasing. So the first condition is met. You can easily check the limit of Bn as n goes to infinity, which is the limit of 1 divided by square root of n plus 3 as n goes to infinity, which is indeed equal to 0. So these two conditions are met. What's the meaning of that? It means that when we plug in 5 over 2, the power series becomes an alternating series, which is convergent. So when we plug in x equal to 5 over 2 into the power series, we have a convergent alternating series. So the interval of convergence so far include 5 over 2 as well. So far interval of convergence is closed interval 5 over 2, half of an interval 7 over 2. Now what about 7 over 2? We did x equals to 5 over 2. Now we need to plug in 7 over 2. Let us check 7 over 2. When we use x equals to 7 over 2, our series becomes, so let me copy down the series. This was our series, original power series. This guy becomes the summation of 2 to the n. Here you have 7 over 2 and starts from 0, goes to infinity. That can be simplified into the summation of 2 to the n times, here you have 1 over 2 to power n. Okay. And you have square root of n plus 3 and start from 0, goes to infinity, and this guy becomes 1 over 2. Well, this guy is not going to be a convergence series. Why is that? Because this can be written as the summation of 2 to the n times 1 divided by 2 to the n. Over square root of n plus 3 and start from 0 to infinity. So you can cancel out 2 to the n, 2 to the n, and this series is comparable to a p series, 1 divided by square root of n plus 3 and start from 0 to infinity. But this new series is comparable to p series 1 divided by square root of n. Let me move this a little bit here. So I can add the series notation as well. Which is divergent. P in this case is a half, and P is less than 1, so you get a divergent series. It means that x equals to 7/2 cannot be part of the interval of convergence. So our conclusion is, so the interval of convergence for the series is half closed, half open interval 5/2 and 7/2. So let us recap what we did. Went over a lot of steps here for you. We started by having a power series. We wanted to find the interval of convergence. We're going to apply the ratio test. The ratio test says the limit of the absolute value of an plus 1 over an must be less than 1. Then we say that we have a convergence series. So if you form the limit of an plus 1 over an and simplify this further, you end up with the limit of square root of n+3 divided by square root of n+4, which is 1 times 2 times absolute value of x minus 3. All must be less than 1. So 2 times absolute value of x minus 3 must be less than 1, or absolute value of x minus 3 must be less than a half, or x is bounded between 5/2 and 7/2. By the ratio test, we know that the convergence for this series is bounded between 5/2 and 7/2, but it doesn't give us any information about the boundary points. What about x equals to 5/2 and x equal to 7/2? When you plug in 5/2, your series becomes an alternating convergent series, but when it comes to 7/2, as you saw, we end up with a P series, which is divergent. So it means that the interval of convergence does not include 7/2. The interval of convergence is half closed and half open interval, as you see here.